Okay, let's start. So today we are going to move on to another topics in machine learning. So last time we did talk about Bayesian learning, right? We discussed about how do you use statistic model in order to solve some simple problems. And we also talk about naive Bayes, which is the simplest way to use statistic in your machine learning algorithms. Now we move on to another algorithms that some of you may encounter when you learn about AI, which is called genetic algorithms. And this is important because, well, you will see it in somewhere in your application. I will show you one particular application after this. And the idea is very simple. We try to mimic the way that the nature works. So, for example, what you see is that in our world, we have a lot of people, individuals, stay in the community or mapping into genetic items, they call it populations. And some people mating and have some offspring, and usually the offspring will inherit some good properties from parents. Well, by properties, I mean some sort of characteristic from your parents. And if in a population some individual are weak and not so good, they will naturally be discarded. Some good individuals may stay for the next generation, right? That's the nature, how it works. And also in the nature, we have some phenomena like some special people appear among us, and sometimes call that one mutations phenomena. Okay, and from that observation, people try to integrate that one into an algorithms, and we call that genetic algorithms. An algorithms that's solely based on the nature of evolution. And sometimes when you read documents in some other books, they call this one evolutionary algorithms. Anyway, this is a study field, a research field that some people interested in. Not everyone, but there's a community for this kind of topics. And I have some friends also work in this kind of topics also. We will discuss about how it will be applied in your application and when to apply it. Not necessary that you are going to apply genetic algorithm for every problem in machine learning, but just a few of them. Okay, so let's start. We are going to talk a little bit about this genetic algorithm first. So, as I mentioned earlier, this kind of algorithms in machine learning based on evolution, and it's very nature, right? It's just simulate how nature works, and the essential thing in this algorithm is searching. When you learn about AI, especially I remember some of you may taking a course called Introduction to AI. In that course, you are going to learn this autumn also, I believe. So I'm going to make it quick. Along of our autumns, we use this kind of genetic autumn for searching for a solution. Now you have to define what is the solution you are looking for. Um, in other words, you are looking for hypothesis in the space of hypothesis. Okay, and mapping between terminology, the hypothesis here is the solution you are looking for. Okay, that can be a set of hyperparameters. It can also be a set of hyperparameters, if you will, or whatever you call it. That's some parameters you want to optimize. Okay, and the computer trying to looking for some sort of hypothesis that satisfies some certain criteria. and we code that criteria implicitly or explicitly, I don't know. But you have to define some sort of function to describe that criteria, and that function is called fitness function. So the role of fitness function is to define the criteria to say if this solution is good or bad. Okay, so evolutionary computations is a combination of genetic algorithms and genetic programming in general. And the process of learning actually it's just searching. You're looking for a good individuals, and each individual will be the solution, right? So it looks like we are trying to do some sort of searching in the space. Well, speaking of the space, you may know that if the number of parameters increase, then the space you are searching will be a lot more bigger. For example, if you have one parameters, that parameters can take 10 values, right? And suppose that you are optimizing a problem worth about 10 parameters. Then the searching space you have will be 10 power of 10. And that is a huge number. It's like how many zero do I have? 10, right? So it's like 10 billions values, 10 billion possible individual in that searching space. So that's huge. And that is why genetic algorithm is not designed for a big problems. Sometimes you only use genetic algorithm to search for very simple solutions in a small space. Okay, so beware of that, and that would be great later when you apply to your projects. Okay, so let's talk a little bit about genetic algorithms in birth. I'm not going to some advanced algorithms here. No, it's just the basic one because you don't need some kind of advanced thing. Okay, so we have to talk about a few terminology you may have in genetic algorithms, GA in short. So in this kind of setting, you will have some sort of elements we call gene, right? A gene is actually, oh, I don't mean to use that red color. How about uh, orange? Gene. The gene is some sort of value that indicate some characteristic of the solution. It can also be, well, it can also be understood as a value in your parameter set, which you are trying to optimize. Okay. And the other terminology we may have is chromosome. Well, chromosome is a set of gene. Okay, it's the whole sequence of gene. So chromosome sometimes be called individuals or hypothesis or solution, your choice. Okay, so a chromosome is encoded values of the parameters that you want to optimize. Okay, and you may have a lot of chromosome, and each chromosome representing some sort of solution. Then the collection of those chromosomes is called population. Okay, and in genetic algorithms, there are some other terminologies like, well, you may know about this figure as some sort of um, mating, right? Two chromosome are going to stay into the next generation by doing mating and making new offspring. So from two individual A1 and A2, you make two offspring A5 and A6, which the content, as you can see, is swapped in the middle. Okay, so that's some simple terminology you may have in genetic algorithms, and there are more to go. So the prototype of this genetic algorithm is very simple, as you may know. At first, you initialize the population. So you define a set of population. The number of individuals is up to you. You are the one who make that choice. Maybe 10, maybe 100, your choice. And for one round, we are going to evaluate the fitness of each hypothesis. Think about it. The fitness is a function that measure the fitness. No, I should not call that. Uh, the good, how good your solution is. Okay. Then we are looking for some hypothesis that satisfied our condition. For example, I'm looking for a good solution, but how good is enough? You need a threshold, right? So why the max of your fitness function is still smaller than this threshold? You keep repeating the evolution process, but if the max of fitness already surpassed the threshold, then you stop because now you may look for a good enough solution. Okay, and then you can start create a new generation and repeat the evaluation of fitness again. That process keep repeating until you satisfy the condition. Very simple, right? So I guess everyone can do this, and well, we have to talk about how do we create new generation in general. So in order to create new generation, you need some sort of algorithms. So we have mentioned here three algorithms, three basic one. First, selection. Second, crossover. Third, mutation. That's three basic one. Now let's talk about the first one, selection. How do you select the individual that can survive in this generation? Well, it's very hard to tell which one is the good one, right? And the only criteria you may have is the fitness. Okay, so the logic here is if some individual, some solution has a good fitness, it has a higher chance to survive for the next generation. But if an individual with a very low fitness, it has a lower chance to survive to the next generation. By no means I'm saying that the good one will survive and the bad one will die. No, we have no definition over that. What we're saying is in the selection process, you select the individuals based on probability instead of the absolute value of fitness. Okay, so you have a higher chance doesn't mean you are going to survive. You have a lower chance doesn't mean you are going to die because that's nature. Good person may die, bad person may survive. That's the truth. And this is why selection algorithms based solely on the probability, and you have to understand that. Now, sometimes a bad solution maybe is the background for the next good solution, sometimes the best solution. So who knows? You have to pick a choice, but sometimes you have to let some arbitrary factor involved in the process. And second, we have crossover algorithms. Okay, crossover algorithms is an algorithm that allow you to make new generation, make the offspring from individuals. There are several ways to do so. Mutation is a way to make your individual become different from what it is. So explicitly, you are going to change some gene inside the chromosome to make it special. Just like mutant, you watch a lot of movie about that, and you see that they have some special ability because, well, some of their gene has changed, so they for some reason have that special ability while their parents doesn't have. That's mutation. And then we are going to formalize those things into formula, as you may see here. First, we calculate the probability, right? We are going to select 1 minus r p hypothesis in p to add to the new generation. And the selection probability will be calculated as you mentioned, as you can see here. Is the fitness of the hypothesis I over the sum over all the fitness you have. All right. And look at this formula. What you see, the sum over this probability is 1, right? If you sum over PR, you take the sorry, sum of probability PR of HI over HI, this one will be 1 for sure, because this is the probability over every hypothesis, every individuals, right? So an individuals with high fitness will have a higher chance to be selected in the next generation. That's the fact. Okay. And you are going to select not every hypothesis, but 1 minus R hypothesis here. Okay. This is what we have. So what is R? R is something that you may want to concern. You may discard a few individuals and you will make some 1 minus R P individuals instead. What I mean is in the next generation, not every individual will survive. Just a few of them will survive. Okay, and R is the factor that controls how many percent will die and how many percent will be reversed, reserved. So let's say R is 30%, then it means you are going to keep 70% and delete 30%. Okay, that's the idea. Now for crossover, again, we have some idea about crossover. Again, we have to select some pair, and the number of pair you are going to choose is R over 2 multiplied with P pair. Yeah, this is the number of pairs you have to make, and you pick up them according to the probability PRS, sorry. So given this one and the pair with the probability you have, you can apply the crossover operator. Well, for crossover operator, you can have several ways to do that. You can either, well, I will talk about it in another slide. Okay, it's a little bit more complicated. For mutations, we just randomly select some gene and we invert that gene. Randomly select one bit to invert that one and make it to be something crazy. Okay, and well, given that hypothesis, you can see that some people can representing decision rules like this as a hypothesis. That's possible. But again, this one is very special because you have to make decision case by case. I mean, in order to form the chromosome, it's very problem dependent. I cannot tell you how to define chromosome if you don't give me the problems. First, tell me the problems. Then I can tell you how to define the chromosome. For example, you have a decision tree, right? And decision tree will decide, make decision based on checking a few conditions, right? And so it's a, let's say, if A1 greater than 1 and A2 smaller than 2 and A3 greater than 5, then C equal 1, for example. This is one decision rule. Then I can formulate this decision rule into a vector saying that, okay, for the first one, I have 1. This one is for A1. This indicate that this indicate the rules that A1 is greater than 1. So how about A2? If A2 is smaller than 2, then how do you represent that one? Can you tell? Well, it's very troublesome because now you don't know what to make here. Sometimes the condition doesn't apply in this setting. So if you want to make decision based on this, then instead of giving a number, then you may want to have some other properties like zero. Well, yeah, sorry. Suppose that I want to represent that greater operator. I will have one here. Okay, so one mean A1 greater than one. Then for A2, I will have uh, 0 and 2 instead. Okay, and for A3, I can have, well, greater, so 1 and 5. Okay, so what you are seeing is a representation of that rules. Okay, I can classify some sample into class 1 if they satisfy the rules A1 greater than 1, A2 smaller than 2, and A3 greater than 5. So that is how we define the gene and chromosome. And that rules, greater or smaller, can be defined by one bit, either 0 or 1. And the other value can be represented by a number like what you are seeing. Okay, so that's representing a root. So if you have a decision tree, for example, decision tree is nothing but a bunch of decision rules, right? And if you collect them and make them into a chromosome, a very long chromosome, then the the process of training is nothing but searching for a good or the best chromosome out there. But that's not easy, you know. I don't see people use this kind of GA for decision tree, but in some very simple application, maybe this is possible. So beware of that rules, okay? Sometimes you can do that. And this is another example. In this example, what you see is that we have a rules. Say the wind is strong, then you are going to play tennis. Then that rules can somehow be mapped into a chromosome like what you are seeing there with like 7-bit. Wow, that's kind of interesting, right? And so if you have multiple rules, you can concat them into a long chromosome, just like I mentioned earlier. All right. And so for decision tree, you can use that to represent your chromosome. Now let's talk about crossover operator. For the crossover operators, you have several ways to do so. Either use single point crossover or 2-point crossover or uniform crossover. It's up to you. And each of them may be different from each other a little bit, just a little bit. So first, for single point crossover, you are selecting one single point. This one, for example. You can choose a fixed point or random point, whatever, and you cut your chromosome here in this point, and then you swap or you twist the gene. No, let's say you twist the chromosome just like what you learn in biography. No, by what is the word? I lost the word. My head is flowing now. Anyway, you twist the chromosome and then you make two new chromosomes by doing this. And because you only select one cutting point, so they call crossover. Okay, that happens in our gene every single day. So that's how we apply it into GA again. For 2-point crossover, the reason why we call this one 2-point is because you, instead of choosing one single point, you choose two. And given that 2-point, you twist on the first point and then you twist again on the second point. So in the end, what you see is that 0, 0 on the bottom will be cut to the top, and again you will see, okay, here, no, 0101 from the bottom will be just to the top. That's how it works. Okay, if this is not enough, sometimes people say, okay, this is not enough, so why don't we make some alternative way? Then they do. They say, why don't we twist the chromosome in random positions? So let's say I cut it here, and then I cut it here, and then I cut it here, I cut it here, here, yeah. So this is very messy, you know. No one will do that, even though this is in theory possible. But in practice, I don't see this one work. You know, swapping the chromosome in one cutting point or two cutting point is okay. That's fine. That's what you see in nature, right? But randomly twist the chromosome is really abnormal, and that is why, even though in theory you can have this kind of method, not many people use it. Maybe some of them will test this kind of approach for fun or just for the ablation study, but by no means they will apply it in practice. And just remember that, okay? Because the upstream may be a mess and it doesn't give any benefit for you in the long run. Okay. Now let's see. All right. There's another crossover operator. Well, this one is a little bit more complicated. Like you swap the gene, the chromosome in some random order, but you make the new chromosome sometimes longer than the old one. Okay, so this is art. At the same time, I see in it because well, sometimes this is not really meaningful for us, even though you may say that it can bring some sort of swapping decision rules between two solutions. But yeah, it's kind of random. You know, it's hard to tell. Is it right thing to do? No, I cannot say anything about it. So again, this is not very popular in GA. Okay, it's available because that the heuristic people propose, but by no means this one is popular. No, it's not. And let's talk a bit about fitness function. Well, fitness functions is a functions defined by you. That means I mean that there's no formula for this one. You are the one who make decision. Is it a good way to evaluate the goodness or the fitness of some hypothesis? The choice. There's no common rules here. And the one that was here on the material is saying that you can measure the fitness by the square of the correctness of the hypothesis. In other words, fitness can be measured as the percentage of training of correct what can I say? Correctly classified training sample over all the sample you have. Let's say I can classify 80% correctly, then the correct of H will be 0.8, and the fitness now will be the square of that number. So the square of that number would be 0.64. That's a number, right? But this is not the only way. There are many other ways. It's up to your problems. Okay. And there's something we have to talk about here is the inductive bias. So when you learn about GA, you may wonder what is the inductive bias in GA. Can you tell? Remember what is inductive bias? Inductive bias is some sort of assumption, the prior assumption that you make before you design the items. Or, in other words, this is the assumption associated with the items, the models. Okay. So in GA, what is the inductive bias? Well, you may think that, all right, the inductive bias of GA is the assumption that your solution can be mapped to the chromosome. That's one thing. But the second thing is the selection mechanism and the crossover mechanism can lead you to a, a good solutions. But there's no guarantee. That's just assumption, right? And there are many other things we have to talk about GA, but speaking of inductive bias in J, there are so many. They pose so many assumptions before you use this arms. Okay, so beware of that, and you will do well. Now, what can I do? I guess I'm going to show you a demonstration of this GA. So hold on. I'm going to show you one particular example. Give me a minute.
Tiếng làm chặt.
Okay, guys. So let's see. I have a video here. Actually, you can find a lot of them like this for demonstrating the purpose of using this one for GA, because the program is kind of simple. It's not necessary to be very complicated at first. So there are some terminology that I believe some of you already know. It's related to neural network, and we are going to talk about neural network after we discuss all kind of basic algorithms in machine learning. So right now, let's just enjoy and see what happens. So we are going to use genetic algorithms in this application. And what you see here, let me explain a little bit. They will define the simple neural network like this one with some input and some output. So what is the input? The input will be 24 input neurons, which is 24 observations you may have of the snake. And there are two hidden layers. Each hidden layer will be uh, 18 neurons. Well, very small, right? This is a tiny, tiny network. And there are four output neurons. Okay, those will make the final decision. So if you learn about neural network earlier, you may know that we have some sort of parameters in the system. Then those parameters will be the one learned by genetic algorithms. Okay. Okay, so give you a bit of explanation on the input. So for a snake, you see that the snake will have the vision. The vision is described by a direction. Okay, their eye will look at the world in a direction in front. And then what you see is that for each direction, you may have the distance to the foot, the distance to the tail, and the distance to the wall. So that three information you may want to know at each direction. The direction is fixed, and now you have to specify the distance. That's the feature you fit into the network. So A by 3 will be 24 values. And then the snake will make decisions. Okay. So again, each generation will contain a population of 2,000 snake. Well, we have a very good computer nowadays, so simulating 2,000 snake is not so hard. It's kind of simple, right? 2,000 snake, and if you calculate the number of parameters in a snake for a snake, it's very small. So there's no trouble in simulation. It costs only time to simulate a snake, so that's fine. Now, as you can see, in the very first few iterations, the snake is very stupid. It doesn't know what to do because all kind of move here is random at first, and there's no way you can control it. It's very random. So sometimes it can eat the food, it's not. What is the fitness function? Well, the fitness function will be the number of food it eats and how long it can survive. In other words, you can consider the fitness function to be the score of the snack. Okay. And you see, in some particular cases, the snack will try to grow, but somehow end up very stupid because the searching space is very wide. But we randomly looking for the solution. Therefore, not necessary for you to end up with a good solution at the beginning. It costs you thousands of iterations, thousands of thousands. As you can see, over generation, some good individual will remain, and it will be fine-tuned over generation. I'm saying fine-tuned because the offspring usually look very similar to the parent. So one good individual will be refined over time by crossover and also by mutation. So playing with those simulation is kind of fun if you are some sort of beginner, I think. It took you some time to learn how to implement those things, but it would be fun. It would be fun. This performance achieved after 23 generations, which is quite good, and the mutation rate in this work is like only 10%. It's quite high, but mutation is necessary. Without mutation, you cannot get a good solution. The music there. So after a while, you may end up with a very good solution. Oh, it's done. So anyway, that's what you have with genetic items, and you can find a good use of that genetic items in many other places. So remember, when we talk about genetic items, we have to consider the sign of the problems. Otherwise, you will be in trouble because, well, speaking of neural network, it's very hard to estimate the parameters, right? And if you use GA to looking for the solution on the highly dimensional space, you may not get the solution. No way. It's very hard. So beware of that. We only use GA for some simple problems, not the complex one. Okay. So that's about it for GA. I guess we are going to move on to another topics today. So how about a short break for 5 minutes and then I will continue with another topics. Okay. Okay. So I will see you in 5 minutes. Okay, guys, welcome back. So let's talk about another topics which very related to our discussion in Neighbor.js. Actually, we are going to make things more general. Okay. In other words, we try to formulate things in a general way. And even though this kind of machine learning algorithm is very classic, you will find it somewhere nowadays, depending on the problems you are working on. Maybe this one is very useful. The thing is, it's easy to implement and also it's very lightweight compared to some other items like LSTM in neural network, if you know about it. So we are going to have the last half of this semester talking about neural network only. But for now, let's just focus on the basic of machine learning. Okay, and yeah, let's see what we have today. We are going to take a look at Bayesian network and what we have in those networks that make them special. And we also talk a bit about neighbor-yes classifier and why is it implemented and categorized in this graphical model topics. And last, we are going to talk about hidden Markov model, which is a very important machine learning algorithms. Okay, I believe some of you may heard about it, but in order to understand, fully understand and utilize them, it takes time. All right, so let's jump into it. So first, we are going to talk about Bayesian network, a network that allow you to modeling thing in terms of math probabilistic. So first, you see that given this kind of direct graph, then you can somehow show the dependency between those evidence, those parameters. For example, C depends on A and B, right? D depend on C, E depend on C, and therefore, for some reason, what you have is a dependency between those things. And if you write some formula like calculate the probability of A, B, C, D, and E, this is the joint probability between all kind of random variables A, B, C, D, E. Okay. Um, in general, we cannot form any kind of relationship here, but thanks to the Bayesian network, it shows the dependency between those variables. Therefore, you can easily form this joint probability as the probability of what? Uh, as you may know, the probability of D given that you know about C multiply with probability of E given that you know C and probability of C given that you know A and B and probability of A and probability of B. So this kind of interesting. You only need the graphical models like this, the graph, and you can easily formulate the joint distribution of all of the evidence you have in the graph just by using the conditional probability. And the conditional probability is what you can gather from your data. You can gather them easily by just counting, depend on the problems, of course, but overall, it's not hard to gather. And we will talk about it in shortly, I think. Let's see. The advantage of this one, as I mentioned earlier, we can have some properties like conditional independence. So looks like the probability of D even CEAB is nothing but the probability of D even C. That's saying the the occurrence of A, B, and E does not really matter to D. D only depends on C. So let's say that D is conditional independence from A, B, and E. Okay, that's how we read it. And you can easily factorize the probability, the joint probability, as I mentioned earlier. The joint probability of A, B, C, D, E is nothing but the probability of D given C, probability of E given C, probability of C given A and B, and probability of A and probability of B. So given all of this, we can do a lot of things from the formula. So let's see. What about neighbor yes? So for neighbor yes, what you have is that you have the probability of A1, A2, A, N. Okay, given the class. So is it familiar to you? The probability of all the attribute you are observing given the class you have is only the product of probability of AI given C with the product of AI over AI. Okay, so if you draw it into a graph, what you have, this is C, the class, right? This is A1. Oh, sorry. May I draw this way? A1. This is A2. And something else like this one, AN. Okay. So you see that A1 now depends only in the class C. A2 only depend on the class C, and so AN. But they are independent given the class C. And neighbor yes solely rely on the conditional independence assumption, right? And so if you modeling the neighbor yes into the graphical model, you will have something like this one. All right. So that's what we have so far, and that's kind of convenient, right? So given that, we can easily see that we can calculate the joint distributions of our data. Now, when it comes to this, we say neighbor yes is a generative models. Now, why is it generative models? Because there is a definition of generative models. Remember, if you have the probability of something like X, can we generate the data? Yes or no? Yes, right? Because suppose that I know that X will be distributed like that. This is the px, the probability of X. And I know for some reason, I know that X distributed along this value like X mean and some other thing. So can I generate X according to this distribution? Yes, I can. How to do that? I can form the CDF of X. In case you don't know what is CDF, you have to learn about probability one more time. But CDF is the integral of probability. So it goes from 0 all the way. No. What can I say? It's integrate like this one and here. So given that, you can randomly generate a uniform distribution in this direction, and for each value here, you can easily get the X here. And if you sampling thing this way, you will see that your data will be generated in the distribution of the shape you have earlier. Maybe my drawing is not good enough, but it goes something like this. It goes like this. Okay, yeah, it's very sloppy here in the middle, and it goes up here. Okay, and this approach one over there. It's somehow very dense in the middle, in the middle of the things. So that is why they say neighbor yes is a generic models because you can easily calculate the joint probability of the class given A1 to with all A1 to AN. This is the joint probability. This is joint probability. Now, if you have the joint probability, you can generate the data. And this one easily formulated as product of AI, property of AI given C and multiply with PC. Okay, and so you have the data. If you have the joint probability, you can generate all the data of all the class you want. Just give it a call and you can have the data. So we see a lot of generic models nowadays. Now, when you think about it, you will have some generic models in neural network as well, like GAN, for example. Some of you may heard about GAN and diffusions, and all of that models in neural network, we call it generative models because somehow it gives you ability to generate the data. Okay, neighbor yes also, but in order to train neighbor yes and in order to generate the data very well, you have to think about the inductive bias of the model. Actually, the inductive bias of neighbor yes is very strong, right? It's assumed that all the property, all the attributes are conditionally independent from the class, which is not valid in our setting. In the real world setting, the attributes are not conditionally independent. They are, for some reason, depend on each other. And therefore, using neighbors in order to generate data is not what they do in practice. But it's good to know that neighbors is also generative models. Okay, even though some of you may use neighbors for classification rather than generate data. All right, so let's go on. We have some other terminology called discriminative models, a model that's used for classifying your data into classes. And in that case, we have several models. And the one that I'm not going to discuss with you in this course is CRF. The real name of that one is conditional random field. It has a wide application. However, if you are going to use conditional random field, then you have to read some paper. I'm not saying that it is impossible to learn it, but first, it was implemented in some framework already. So if you want, you can use that. But in order to use it, I suggest that you have to read about it in some original paper or in some other blog to understand how it works. Okay. Now, um, let's see. So, what about conditional random field and some other discriminative models? What it modeling is this one, the probability of a class given the data. Okay, a class C given data. So if you can somehow calculate this conditional distribution, then it's easy for you to decide what class your data can be classified into. Okay, and right now, we finished with some basic one, I guess. Not much to discuss here because everything you already know. So let's talk about one thing that is so important in our course. It's called hidden Markov models. And this one is very important techniques that a lot of people may use for about 30 years or even longer. Who knows? It's very important. By the way, in this session, we are going to talk about a few things. First, I'm going to introduce about hidden Markov models to you guys, give you some example, and yeah, we will formulate hidden Markov model using some assumption, and then we are going to discuss two items very important in hidden Markov, and we are going also to discuss about how to train the hidden Markov model as well as some application of that one. Okay, let's jump into it. First of all, this is one of the most popular graphical models that people use. I'm not saying this is the only graphical models you have, but I'm saying as we use it a lot. Okay, and it's actually an extension of Bayesian network, right? This is why I discussed with you about Bayesian earlier. And it's also a sequential versions of Neighbor-Yes classifier. Wow, if you think about it, why Neighbor-Yes? Because for Neighbor-Yes, it goes like this. You have the class over there, something that you predict, and this is the observation, the data you have. Okay, and the data you have is somehow independent from the class, so you have that bias assumption. But for Markov models, hidden Markov model, what you have is something like this. It's a sequential model, and it's based on the hidden Markov assumption. So what you see is that okay, the observation you see only depend on the the hidden state on the top. Okay, and the hidden state now can transform from one to the other. In other words, uh, transition. I would use that word. The state can transition from one state to another state. Okay, and yeah, I think we have to talk about it in more detail just right after this one. Okay, so this one particular example is very classic. I didn't change it because there's no need to. Okay, so we have a student, and you come to my class for Sunday, and I observe you, and I see that you have something on your face. It's telling me that you are tired, you are hungover, you're scared, and someday you are just fine. So that is my observation. That's what I see in you. Okay, and then I know my student did something last night. Okay, assuming that the activity that he did last night can only be a few, like um, watching TV, go to pub, or just let's say go to the party of your friends, or just yeah be a good student, study at home. Then given those hidden state and given the observation I have, what I'm interested in is what can I tell about your activity given the observation I have. So, for example, I see yesterday you are tired. No, the day before yesterday you are tired. Yesterday you are also tired, and today you are scared. Then my job is to trying to predict what did you do in the last 2 days and today to make you feel so bad like that. And that's the problems of hidden markup model. Trying to predict a sequence of hidden state given a sequence of observation. Okay. And this is why we have some example like this. Okay. You can read more here. Um, well, I guess I don't need to explain about this because it's on the material anyway. All right. So let's talk about the models. The model is saying that your luck only depends on what you did last night, right? So there is a dependency between the observation. This is x at time t only and only depends on the hidden state at time t. Okay, so that's saying your luck only depends on what you did last night. All right. And second, you have another assumption. That assumption say your activity in a night depends and only depends on the activity that you did last night. In other words, we have a state yt. This depends only and only on what you did earlier. Okay, even if you have a lot of activity earlier, I don't care from y0 to yt minus 1. So this assumption say the probability of having yt given y from 0 to, or maybe you want to set it to 1, that's fine. y1 to t minus 1 only and only equal to the probability of yt given yt minus 1. Okay, so that is markup assumption. The past, maybe a lot of things in the past, but I only care about the previous nine. Okay, what I have, what activity I do today, only and only depends on what you did the day before. Okay, so that's two important assumptions of hidden markup models. And here is a formal definition of hidden markup models. What you need in hidden markup model is a finite set of possible observation. Okay, a finite set of observation. Given that if you map into our setting, we have this one is tired, hungover, or scared, and fine. Oh, sorry. No, this is not good. Okay, so that's for the first one. How about a finite set of hidden state? A finite set of hidden state in our example, you will have watching TV, go to pub, go to party, and go to study. Okay, so you have a set of observation and you have a set of hidden state. Now, your job is to find the most probable sequence of underlying status or underlying state y1 to yt given a sequence of observation x1 to xt. Okay, and that was easy or not? Yeah, not so easy, right? We have to formulate this one in terms of formula first. Now, before we do that, let's make some definition. First, you need the transition probability. That is the probability of transition from one state to the other. For example, here you have the topography of the network. Okay, and from this network, what you have is that okay, if the last night you go to party and the chance of the next day you watching TV is 70%, and if last night you go to the party, the chance that today you are going to another party is very low, only 5%. The chance of you go to party and then today you study is 20%. That's reasonable, right? And so on. So you may have a lot of probability here. Just to know that, yeah, you can transition from one state to the other state. And this topography show that how you um, I'm sorry, how you transition from one state to the other. Well, why this is so important? Because not every system can transition from one state to the other fully like this. For example, I may have a system saying that, okay, if today I do party, the chance of I go to pub the next day is zero, then you may not have this link. Okay, maybe if I go to the pub yesterday, then I'm not going to the party the next day. If that is the rules, then you don't have the link here. So again, the topography is so important. It shows that how you can transition from one state to another state, and you have to be clear about that. Okay. All right. Another probability that you may need to know is that it's called emission probability. For emission probability, it shows you the chance of observing something, even you in a status. For example, you have the probability of tired, observed tired, given you did party last night is going to be 30%. And there's some other probability of observing hungover, even you go to the party that was 40%, and the probability of being scared given party you go to party is 20%, and the probability of you being fine even you go to the party last night is only 10%. It depends on people, right? But the statistics say that. So that's something we need to prepare. Now, some people may ask, what if I don't have those number? What can I do? Well, if you don't have those number, you just make it up. But now, let's not talking about it because we are going there very soon. We are going to talk about how do we calculate those number later. Now let's just assume that we have those number and we are looking for a way to calculate the sequence of hidden state. Okay, so let's get ready. There's something you may see. The sum over transition probability should be one. I mean, if you count the transition from party to party, the party to study, the party to pub, and party to what? Um, sorry, let's see. Ah, yes, this one. Party to TV, party to study, party to pub is sum up those numbers should be one. If I pick up another color, let's say TV, I transition from TV to TV 40%, from TV to pub 30%, from TV to study 20%, and from TV to party is just 10%. So you may get this sum to be 1. Okay, and you may encounter, let me choose another color. Well, yellow. So from study to study is the 0.5. From study to TV is 30%. From study to pub, 40%. And from study to party is 25%. And finally, I guess, no, I don't like that color. I guess, yeah, maybe this color. Okay, so from pub to pub is 0.5%. From pub to party is 10%. No, 5%, 10%, and here is 60% to watch TV, and you have, let's say, 25% to go study. Okay, so that's what we need, and that's so important at the beginning. You need to form a table of transitions from playing together. Well, maybe I need to write this table now, just the transition table. Let's see. Okay, let me fill out those number for you. So I have from where is the from and where is the to? Which one do you prefer? You make a choice. Okay, I I I don't force you to put the table in any order. You make your own choice. So let me have this is y t minus 1, and this is okay. This is yt. Okay, so I may have party, TV, pub, and study. So I have here is party, TV, pub, and study. So I will fill the number here in this table for you. From party to party, it should be 0.05. And from party to TV, it's going to be 0.7. To pub, it's going to be 0.05. To study, it's going to be 0.2. Okay. From TV, I will have TV to party is 0.1. TV to TV is will be 40%. TV to pub is gonna be 30%, and TV to study is gonna be 20%. For pub, well, you have pub to party is 0.10%, right? And pub to TV is 60%. Pub to pub is only 5%. And lastly, pub to study is 25%. And finally, you have study to party is 40%. Study to TV is 30%. Study to party is, oh no, study to pub is 40%. No, no, no. Oh, wow, I did it wrong. I'm sorry. Study to party is 25%. Okay. 25, 30, 40, and oops, sorry. Well. I have a number here. It should be zero. Yeah, 5%. Okay. So you got it here in the process. If you don't know, yeah, we got this table. Okay, and given those table and another table for transitions, no, for emission, we are ready to derive some theorems. Okay, so well, based on a lot of assumptions, and what we have is the hidden Markov assumption first, the probability of observing, well, the probability of staying in the hidden state yt depend only and only on the previous state yt minus 1. Okay, and the probability of observing xt given yt and all other evidence or all other observation is only the probability of observing xt given yt. So that's some hidden Markov model assumptions you need, right? Now, what we do next is discussing about the genetic models setting. Well, we say that hidden Markov model is a genetic model because it can help you to calculate the John distribution. Well, the John probability, sorry, the John probability of the hidden state Y and the observation X is nothing but a product. Well, you can easily form it this way. Let's read. This is Y1. This one gives you X1, right? And Y1 gives you Y2. Y2 gives you X2. Y2 gives you another Y3. Y3 gives you X3. And this keep going until this is yt minus 1. And this gives you xt minus 1. And this one lead to yt and xt. So given these graphical models, again, we back to the graphical model. Given this graphical models, the probability, the John probability of all things you are looking at is nothing but the probability of this conditional probability, the probability of observing xt given yt multiplied with the probability of transition from yt minus 1 to yt multiplied with the probability of observing xt minus 1 given t minus 1, and so on. So you can easily form the formula that we see down there. It's nothing but the product of the John, the transitions, and the observation, the emission probability. Okay, so that's very simple and easy. And this is why we say graphical model is very useful in other problems, in a lot of problems in machine learning in general. And hidden Markov model is one particular application of that. And the probability of transition to y1 given y0, you don't know what is y0, but that is the starting point, right? So this conditional probability is nothing but the probability of observing y1 as the first state. Okay, so that is why we call this generative models, because you can easily calculate the chance probability between the hidden state and the observation. Now, given that you can generate any distribution of the hidden state and the observation, in other words, if you have, well, a sequence of activity, like, think about it, you are working in an environment like companies, and you have some activities that you have to perform, like coding, meeting, and then meeting, and then coding, and then meeting the customer, and so on and so forth. So you have a lot of activity, right? So the activity you have is like the hidden state in the hidden Markov models, right? And the activity you do today may only depends on the activity you did yesterday. Now, let me assume that this is true. Then, um, what to do next? You can gather the data from your employee. You can observe, okay, yesterday we do coding. What did he show up today? Maybe he is so tired because of coding, or he feels so bad, he feels so depressed because yesterday you have a meeting with customer, something like that. Or is he angry, or he did something like that, who knows? But you can gather the data, and then if you gather the data, then you can generate all kind of data you may have. For example, I have a sequence of activity, like meeting and then coding for 4 consecutive days, and then meeting and then meeting customer, and so on. So given that sequence, what I am interested in is how many people, in my organization can show up with different observation. And I want to minimize the risk. I don't want all of my employee be depressed, or being very tired, or being very unproductive. If that is the case, if the major of my customer, sorry, the major of my employee, if they show up very tired and very depression, then I would like to change my way of doing things. I would like to change the sequence of activity I perform during the weeks. And sometimes it give a big difference in the performance. So gathering data and being able to generate the data from the models is very handy at some point. And given that, we found a good use of hidden Markov models. All right. And that is how we utilize that one. But the other application of hidden Markov model is to predict a hidden state. So maybe you don't know what happens, but you try to predict what happens. And that is what we are talking about. Okay. And it's very different from the conditional random field, because the conditional random field and other discriminative model trying to modeling the conditional distribution P of the hidden state given the observation. And yeah, that's not what we are interested in hidden Markov models. So we are going to skip it. But remember, I would love for you guys to read about conditional random field, because it's gonna be very popular in some application. So maybe when you read paper and they mention about conditional random field, even nowadays, there's still some paper use that techniques. You will see what I'm saying. Okay, so I guess that the plan today is to discuss some detail, but I would save a bit of your time for calculating later because we will have a demo for how to calculating those hidden state layer. So let's talk about it next class. But today I would like to give you a brief introductions of this algorithm. The first algorithm we are talking about is called forward algorithm. So the forward algorithm say, let me calculate the probability of wait a minute. Let me have all kind of observation up to time t, and then um, the state at time t is equal to the argument max over y t that can maximize the probability of yt given all the x you observe from x1 to xt. Does it make sense to you? Yes? So at time t, you can only predict the hidden state t based on the John probability of that hidden state given all the observation you have. Okay? And because of this, you will see this is kind of greedy. This is a greedy algorithm because if you specify yt right now at time t, then the sequence of prediction, the second y1 to yt, maybe it's not the optimal sequence. It's not the optimal one. So this algorithm, this forward algorithm is called a greedy algorithm. By its basic, it is a greedy one. Okay? And then I would like to expand it once by adding up one hidden state, yt minus 1 into the formula. And you know, if you learn about statistics before, this one equal to argument max over yt. Now let me add p of yt, and I want to add one random variable yt minus 1 into the formula. Then that will be the sum over yt minus 1 of p yt and yt minus 1 and x from 1 to t. Is that okay? Is that clear to you guys? This one is supposed to be the basic of probability you have learned so far, I suppose. So given that, and given the hidden Markov models that you learned so far, what happens? So what you see is that the probability that we are trying to calculate is the probability of this one, and the whole thing here, right? So it's equal to, according to the graphical model you have, is equal to the arguments max over yt, of course, of the sum over yt minus 1, of course, of, well, the probability, the John probability that you are seeing is nothing but the probability of x t given yt multiply with property of yt given yt minus 1 multiply with the probability of yt given, oh sorry, it's not yt, yt minus 1 given x from 1 to t minus 1. All right, so given this one, given this one, what you can take out, you can have is equal to, let me take out yt, okay, xtyt. So it's equal to argument max over yt of probability of what? Yt, no, xt given yt and multiply with the sum over yt minus 1 of probability of transition from yt minus 1 to yt and multiply with probability of what? Of yt minus 1 and x from 1 to t minus 1. But this term is some sort of similar, right? You see this one repeat in patterns. So they form a term called alpha t of yt. That term saying, okay, now what I have is yt equal to argument max over yt of alpha t of yt is equal to argument max over yt of what? Of p xt given yt sum with multiply with sum over, sorry, yt minus 1, okay, of p yt given yt minus 1 multiply with alpha t minus 1 of yt minus 1. Well, now we end up with a very good things. What is that things? That is the formula that you need, right? A recurrent equations. It's a way for you to define alpha t of yt from alpha t minus 1 of yt minus 1. So you can start from y1. Okay, y1 will be the argument max of alpha 1 y1, and then you compute the alpha 2 of y2, and you can specify y2, and that keep repeating over and over again until you reach the final state yt. Okay, and because you go in one direction, you go forward only, this order called forward order because of that reason. So you have to remember this is a greedy orders. Second, it is going in one direction, so we call it forward orders. Okay. All right, so I'm going to show you how to calculate in detail later, and also we will discuss about another algorithm for hidden Markov models and how to train the hidden Markov models. Okay, that's it. And I will see you next time. All right. Do you have any questions? Is this clear, or you need any other explanations? Just tell me, please. Okay. Yeah, I wish someday we have an on offline class. Yeah, we may have one offline class to take the midterm because I need to meet you guys. Right? Remember, we have a midterm after we discuss some basic of machine learning. Okay, and yeah, I will announce that later, not yet. So don't worry, we have a long time because your class start a little bit late. So I'm going to see you later. But right now, if you have no other questions, then yeah, I can finish today class. And thank you for joining. I will see you next time. Okay, see you guys. Yes, I will upload the slide on BKL later. Okay, don't worry, I will. All right, thank you guys. See you later.